Hi, Steve here, and welcome to part 3 in my series of tutorials on the Modo 701 particle system. In this video I will look at the particle operator. The particle operator is a kind of plug-in or co-processor for the particle simulation. Its job is to modify particles. It can change, for example, the position, age or ID of a particle. It can also kill particles. Let's add a particle operator. The particle operator comes in 4 different types, so should really be thought of as 4 different kinds of plugin. The types are assign, integrate, new and trigger. I'll explain each of these types by means of some examples. Notice that the connection between the particle operator and the particle simulation is purple rather than the usual white colour. You've probably already seen this before when we were connecting up the emitters to the particle simulation. The purple connector tells us that this is more than just a simple producer-consumer relationship. It is a bidirectional connection where the particle system can send data to the operator and vice versa. Particles have a large number of so-called features. These are the attributes or properties associated with each particle during its lifetime. For a particle operator to manipulate a feature, we need to add it. Features include things like position, velocity, age, and so forth. As you can see, there's quite a lot of them. Notice the features come in 2 different varieties. There are read-only features and the normal features. If you're only intending to read the values of a particular feature, it's recommended to use the read-only features. This is for efficiency purposes, but there are some other good reasons why you might want to use read-only features as well, and I'll come to those. I'm going to add position. I'll click the Add to Schematic checkbox to make sure it gets added into the particle operator. You can always add things in afterwards if you forget to do that by selecting them in the channels and dragging them across. I'll set the operator type to new, and this means that every time a particle is created, the particle operator will be activated. Let's also add in an emitter, otherwise there aren't going to be any particles and the whole thing's going to be rather boring. I'll use a surface emitter. And I'll connect in this exciting geometry that I prepared earlier. And notice how the particles are being emitted. Nothing out of the ordinary is happening because we haven't connected these features up to anything. Let me just connect up a math add into the y coordinate, and let's set the value to say, I don't know, 0.25 meters. Well, again, nothing seems to be happening. Now this is something to be really aware of when you're connecting up things to particle simulations, and that is that there's an order that these connections get invoked. And here I have the surface emitter happening after the particle operator. So this particle operator that's looking for new particles isn't going to see any because they're created after the particle operator has been invoked. We want these connections to be the other way around. Now normally when you see the particle simulation, these connections will be collapsed together so you can't see the order, so you have to press this little triangle to get the order you're after. We can reorder the connections thusly, And now, finally, we have our emission offset by 0.25 from the surface. And clearly if I change this value, I can adjust the offset accordingly. This is all well and good, but a fixed Y offset is not very useful. Suppose the surface were curved like this prototype Dalek head. I'll just swap out the square and add in the Dalek. It's not actually very easy to see what's going on here, so I'll reduce the emission velocities to 0, and then we can see exactly where the particles are being emitted from. So as you can see, because we're using a fixed Y offset, the emission points have been completely flattened out, and we don't see any of the shape from the original source. Well, we can fix this by, instead of just setting Y to an explicit value, set it to the original emission point's Y coordinate plus the offset. Let's see how that's done. First I need to add the read-only versions of the position into the particle operator. And what I like to do is separate these off so that they can be conveniently positioned, and then we don't end up with a tangled web of interconnections. And now the particles are being generated offset from their original position by the amount specified. I like to keep things tidy, so let's get rid of these channels that are not being used. If it turns out later on you need them, then it's easy enough to add them back in again. Brilliant. So now we can see why it's useful to have read-only parameters. One reason is purely cosmetic. We can split off the read-only parameter, and then it makes laying out the schematic much easier and tidier. And the other reason is that if you try and take the output from the non-read-only position and feed it back in, that doesn't seem to work. So if you're doing this sort of read, modify, write kind of behavior, it's always a good idea to use the read-only to get the value, modify it, and then write it into the general feature. But hang on, I hear you cry. That's not really what I wanted either. What I wanted to do was offset the particles normal to the surface of the emitter. Well, we can do that if we use the velocity. So I've cleared out the schematic here, and I need to add in the features that I want. Let's add in the position again. And separate those off. And add in the general position. And finally, add in the velocity. We're only going to read this, so we'll have the read-only version. Let's separate those off. So what we want to do is add the velocity onto the position, but of course the velocity is not a constant magnitude, so we need to set it to a specific length, and there's a very handy vector operator called setLength. So we'll use that. And now we can take our vector in. These are a bit fiddly because they have so many connections. So that will generate a vector of a particular length, and we can use the length parameter of setLength to control our offset. We just finally need to wire this up, connect the positions to the scaled length, and then wire it into the particle operator. So we need a vector add. Again, bear with me whilst I connect all these wires up. And finally set the position with the particle operator. I'll tidy things up a little bit so we can see what's going on. Being a programmer, I prefer to write source code to editing diagrams, but at least with diagrams you can't make silly syntactic errors. There, that doesn't look too bad. Okay, with any luck, when we press the play button, we will get our particles offset in the way that we're anticipating. Well, that's rather disappointing. There doesn't seem to be any particles created at all, or maybe they're being created somewhere silly. And the reason is that earlier on I set the velocities to 0, so scaling a 0 vector isn't going to work at all. So we'd better set the velocity to something sensible. It doesn't really matter what we set it to. And now the particles are being created correctly offset, and we can use this length parameter to change the offset. Let's change it to 1/2, for example. Okay, but so far all we've really done is re-implement the offset channels that already exist within the various emitter types. However, the particle operators are very flexible, and we can feed any function we like into the offsets that we're generating. So here I've cooked up a magical function called sync2d. It doesn't really matter what this function does. All we need to know is that we feed in a couple of parameters, the x and the z in this case. It does something to those parameters, and then the result is fed into the y offset. So I'm sure you're very eager to find out what it does. I'll press the play button and all will be revealed. It generates this sort of jelly plot effect. In this last example of using the new mode of the particle operator, I have modified the velocity of the particle to restrict it to the xz plane, so that the particles will have no velocity in the y direction. So how have I done that? Well, I read the velocity, I calculate the magnitude of velocity so that I can preserve its size, and feed that into the length parameter of the setLength function. I then feed the original x and z components of the velocity into the setLength and set the y component to 0 using this add function. So the resulting velocity will have the same magnitude as the original velocity but with no y component. We just feed that into the velocity in the particle operator, and that will be adjusted within the simulation. So I'm using a particle generator to generate a single point, which will be the source of the emission. You can see the particles are now restricted to the xz plane. I've just put another flourish into this example. I've put some animation on the channel of the source emitter for the emission rate. So if I play it over time, we end up with concentric rings of emission. Let me just show you the animation for the emission rate. So from time 0 to time 12 we have a very high emission rate, and then 0 from 12 to 24, and repeat. Okay, I've spent quite a long time looking at the particle operators in the new mode, but what about the others? The next I'm going to look at is assign. Here I have a particle operator which I've renamed, helpfully, accelerate spin, and as you can see it's in assign mode. This means that the particle simulation will invoke this particle operator for every particle at every step during the simulation. So each particle at every step we will read the y velocity, add 0.1 to it, and then write it back into the angular velocity. So the result should be that the angular velocity will gradually increment with time. Let's play the simulation to see what happens. As you can see, the particles are getting faster and faster as they age. I've plugged the results of the particle simulation into a replicator with a prototype object so that we can see the spinning. If we just showed the point particles, then we wouldn't be able to see the spin. This idiom of incrementing a value every time around the simulation is very common. We take it for granted that the velocity is added to the position and the angular velocity is added to the rotation for each step. If you find yourself incrementing features like this, then the integrate particle type is what you want. I've simplified the spinner example by changing the particle operator to the integrate mode and just feeding in a constant value. This value is scaled according to the particle simulation step time and added to the angular velocity each time around the simulation. This means that we don't need to explicitly read the angular velocity, but that we get more or less the same effect. As an added bonus, the diagram is a lot simpler. This next example is due to Chris Haig, who kindly posted it to the forums. In my opinion, it's a godsend. Currently, replicators have no notion of time. So we can't use the particle age to control, for example, the color of the meshes when they're rendered. Replicators, however, do understand particle IDs. So if we can convert particle age to particle ID, we can use the age indirectly to drive a curve. Now, age is in seconds, and ID is normally in the range 0 to 1. Thus, to convert, we need to multiply by the frames per second. That gives us the particle's age in frames, and then if we divide by the number of frames, we should get a number in the range 0 to 1. So in this particle operator, which I've renamed age to ID, I've added the ID as a read-write feature and the age as a read-only feature. The age goes through these transformations and gets written into the ID. The replicator will pick up those IDs, and if we create an item mask for the replicator, we can use that to drive a curve. To create the item mask, we right-click on the replicator and click on Create Item Mask. I've already done that in this model, so I'll go straight to the shading tree. And here we have the gradient with its curve in it for mapping the ID from 0 to 1 to the corresponding colours. And we're driving the diffuse colour from the gradient. If I run the simulation, we won't see anything very exciting in the normal view. In order to see the effect of this, we're going to have to render these particles. So I'm going to have to use some machinery that I haven't shown you yet, but what the heck. Before rendering a particle system, we must first bake it using this mysterious third green button down here. We have to specify the start and end time for the baking, then just hit OK. And because this is a very simple system, the baking takes no time at all. I can now bring up the preview window with F8. And if I scrub the timeline, we can see the particles as they get older change their colour in accordance with the curve. Just the job. The last particle operator mode is trigger. As you might expect, this lets us explicitly control when the particle operator does its business. In this rather contrived example, I'm using a random number to trigger a change in the velocity of the particles. So when the particle operator is triggered, I set the velocity in the y direction to -1. And if I just play the simulation, you'll see what the effect of that is. Every now and again, a particle will be commanded to fall out of the sky. I can adjust how often the raining happens by changing the threshold. I've cooked up a random number seed from a combination of the particle ID and the time. So I've scaled the time by a factor of 10 and added in the particle ID to get a unique seed for each particle. And that means that we'll get distinct random numbers for each particle at every time during the simulation. I'm not sure this is of any great use to anyone, but it does at least show how the trigger mechanism works. The last thing to show you is the kill option. Kill works in a similar way to trigger. When a condition becomes true, the particles are destroyed. In this very simple example, I read the y position of the particle, compare it with a threshold value. If it is less than that value, then the particle is killed. So at the moment, the threshold value is 0, and particles are destroyed when they reach the ground plane. But I can change this value to anything I like. Kill the particles higher up. This last example is the bee's knees. The aim is to have the particles point in the direction in which they are moving. If you think about the way that things move in the real world, this is exactly what you expect to happen. If you see a seagull flying through the sky, you expect its beak to be in the direction that it's travelling and not pointing to the side or to the rear. If you look in the Modo 701 preset, you'll find some fairly sophisticated preset assemblies that do just this. What I've done for this example is pare it down to the bare essentials so that we can get a quick grasp on how it works. Let me run the simulation just so that you can see what's going on. So the particles curl over as they reach the apex of their travel and then point down as they fall into the ground. Let's deconstruct how this rig works. We're using a particle operator, obviously, because that's what this video is all about. And the particle operator is in the assign mode. That means that we're going to update the particles for every step of the simulation. And what are we going to update? Well, we're going to update the rotation, because that's what's going to describe the heading of our particle. In order to align the particle to the velocity, clearly we were going to need to read the velocity. So we've patched in the velocity feature into the particle operator. The core of the rig is this direction constraint. The direction constraint creates a rotation matrix from a couple of other matrices. These matrices describe an origin position and a destination position. Okay, so far so good. How do we set up those from and to positions appropriately? Well, it helps here to know a little bit about vectors. This velocity vector here, describing the velocity of the particle, can be converted into a position simply by constructing it using this matrix construct. That takes an x, y and z and constructs a position matrix. That position is relative to the origin if we're to treat it as a vector, so simply leaving this position from unplugged is going to create the appropriate from point for our to point. We then plug the rotation into the particle operator and it updates the rotation appropriately. Right, I think we're nearly done. I'll just show you where to find the matrix construct and the direction constraint objects. You'll find the constraints under channel modifier constraints, and direction constraint is the top item, and similarly the matrix construct is found under channel modifier matrix and then matrix construct. Well, that's it then. I've shown you the 4 types of particle operator and how they can be used to influence particle birth and evolution. Clearly there are many more features which could be used in all sorts of creative ways, but they must wait for a future episode. So thanks for watching and see you next time.